So I think you can start. So my name is Konrad Kamiński. I work for Allegro. And today we're going to see how we can write asynchronous code with Kotlin coroutines. So first I just want to ask one question. So how many of you actually know Kotlin, the language, like have read about it or done some programming? Right, okay, so about like half of that. So I ask because there will be some code shown here, actually quite a lot of code. But if you're familiar with Java, you should be able to understand it. For some more difficult stuff, I will try to give a more deep explanation. So we're actually going to start with some code. So here you have a simple function. This function tries to send an audit message to some external system. So what it does is, for a particular user, it first tries to get the account ID, which is assigned to that user. Then it tries to get the number of products which are assigned to this account. And then it sends a message. So this function is quite simple because there are just three things happening in sequence. And so just by looking at it, you know immediately what actually happens. Now, there's just one problem with this kind of code. So let's imagine that these functions like getUserAccountID, getProductCount, and sendMessage, they all go over a network to do something. So for example, they fetch data from some microservice, or they fetch data from a database server. So it means that at some point they have to send a request, a network request, and then they have to wait for the response from that server. And these methods here, they are blocking methods, synchronous methods, which mean that a thread that executes this function will be blocked, waiting for the response from the server. And no, it's not really a problem if you have a couple of those threads, but today we actually develop services or applications which serve millions of users. So if we want to serve millions of users with this kind of code, then we will end up with millions of threads which can actually essentially do nothing but wait for the response from some other server. And actually, it's really not doable on contemporary machines because threads, they take resources. So yesterday, Adam Dubiel had a talk about threads and the cost of the threads. So just to recap what he actually told or some the things that are connected to this presentation. So threads, for example, have some explicit cost like a stack, which is needed for each thread. And it's about 1 megabyte by default. And there are some implicit costs like context switches. If you have many threads, then the cost of context switches between threads becomes really very big. So we can't really write applications with that scale with this kind of code. So what should we do? So we have to turn into some form of asynchronous programming. And it comes in many shapes. So for example, we can use callbacks. So with callbacks, our functions no longer return a value, but they have this additional parameter, a callback. And once the result of a function is available, that callback will be called with the result of the function. So here, for example, it's the same kind of code that we've seen before, but with callbacks. And the callbacks here are actually used, are created with Kotlin functions. And you can see that each of those functions, like getUserAccountID, getProductCount, sendMessage, they all have this additional parameter, a callback. And our code looks a bit different now because we have these nested callbacks. And so it's not as nice as it was before. What we have here now is something which is called callback hell. So if you've done any programming with JavaScript, for example, it's quite a prevalent problem in JavaScript. So you have those curly braces at the end of your functions, and your code looks a bit like a tilted Christmas tree. And this is actually a code with callbacks for a simple code which just do three things in sequence. But if we wanted to introduce things like conditional statements or loops or exception handling, then the code would be really very difficult to read and write. So this is actually not a solution for our problem. So there are other solutions. So, for example, you can use something which is called a promise object. And it actually also comes in many forms. So here you can see the code with completable future, which is a promise object which is available in the standard JDK. And with promise object, what you have is your methods no longer return a value. They also don't have a callback parameter, but they return this promise object, which is like sort of like a wrapper around the value. And once that value is delivered, so once we know the result of the function, we can do something with that result. So here we, for example, have these functions like then compose and then accept. And there we can actually specify what should happen once the result is available. So in our case, we'll just call get product count or send message. And promise objects are a bit better than callbacks. So we don't have this callback help problem, but we have other problems. So the first one is actually visible here. So you have to learn all those functions on the promise object. So for each promise object, there's an API which you have to use when you want to some things to happen, like if there's an exception, then do this. If there is a return value delivered, do this. If there's a timeout, do this. So essentially, we have like a number of those methods. They are called combinators. And for each type of promise object, there's a different set of those combinators. So if you know methods of completable future, and now you want to use, for example, Rx Java or reactive streams, then you have to learn a new set of API. So this is really a problem. The other problem is that now our code doesn't really look as nice as it did like before with like regular code, because here we mix two things. We mix the business logic, which is these functions, get user account ID, get product count, and send message, with infrastructure logic. So with these combinators. And this makes our code less readable. So it's really, it would be nice if we were able to actually write like a simple code like the one that we've seen at the beginning of the presentation. And in Kotlin 1.1, there's a new feature which is called coroutines. So actually, it's a new feature in Kotlin, in the language, but the concept itself is quite old. So it's been around for like 50 years or so. It's been introduced in the similar language. And in Kotlin, coroutines are created using suspending functions. So a suspending function is a function which can suspend its execution and then resume it once something happens. So, for example, in our case, we have now our functions now are all suspending functions, so they have this suspend modifier. So it means that they can suspend at some specific points. And in our case, in the send audit message can actually suspend its execution when it calls other suspending functions like get user account ID, get product count, and send message. So it can suspend its execution, and once the result value is available, it will resume the execution. Now, when I say suspend, I don't mean that the thread that executes this function is blocked, because essentially with coroutines you don't block threads. So the question is, how is it actually achieved? And to understand that, we have to go a bit deeper. So we have to look at how the Kotlin compiler generates the code for these kinds of functions. So the first thing that we have to look at is the signature of the method. So when we declare a suspending function, the Kotlin compiler generates a bit different function. The signature is a bit different because this function has this additional parameter, which is of type continuation. And the return type actually right now is any with a question mark. So the question mark in Kotlin means that the value can be null. And any is essentially the same thing as object in Java. So our function now can return any value, including a null value. And we have this parameter, I called it callback, because essentially it is a callback. So before we've seen the code with callbacks, but the callbacks were those functions. Here they are in the form of an interface. And this interface has two methods, resume and resume with exception. And so the idea is that if your suspending function suspends its execution, then it will return the true value with the usage of this callback. So it will either call resume when it wants to return a value, or it will call resume with exception when it wants to say that there was an exception thrown from this function. But sometimes our suspending functions can just want to return the value directly. And then they are actually able to do so because they can return any value. So they can not suspend, and they can just return the value. Now, the caller of our function has to distinguish those two cases where the value is returned directly or indirectly via the callback. And this is why there is a special value, which is called coroutine-suspended. It's like a marker value. And if our suspending function returns this marker value, it means that it suspended its execution. And the caller now knows that the return value will be delivered with the usage of this callback. And if it's not a coroutine suspended, it means that it's just the return value of the function. So how does the code generated by the compiler look like? So here is a code which it's not exactly the code that is generated by the compiler. It's a similar one. So here we don't care about the case where the values are returned directly. So we assume here that always the value is returned via the callback, so the suspending functions always suspend. So the Kotlin compiler for each suspending function creates a state machine, and this state machine holds the state of execution of our suspending function, because the function can suspend its execution at some point, so it has to remember the state of this execution. So what's in the state machine? There are things like parameters of our suspending functions, like user ID here. There is a callback. So suspending function has this additional parameter, a callback, and we have to preserve it so that once our suspending function wants to return the value, we will use this callback to return that value. And here it's called send audit message callback. There is label. So label actually says roughly in what line of code we actually suspended the execution. So from what line of code we should actually resume the execution of our suspending function. So we're going to actually see it later in more detail. And we also have, in our state, we have the values of the local variables. So account ID and product count in our case. So what happens during the execution of our suspending functions? So first, the label value is 0 because we just started the execution of our function. So what we do is, in the 0 state, we want to call getUserAccountID. But after that, the execution of our function should resume from the place which is after getUserAccountID, which is this is why we set label to 1, so that once we resume the execution, we will resume it from the place in the code which is after the getUserAccountID. So we set label to 1. We call getUserAccountID, but getUserAccountID is actually a suspending function, so it needs this additional parameter, this callback. And you have to provide one to this function. And this is actually where one trick takes place. So state machine actually implements continuation interface. So you can actually reuse the same object, the same state machine, for all calls to suspending functions in our send audit message. Before, when we saw this call with callbacks, with these nested callbacks, for every callback, we would have to create a separate object. So in our simple case, we would have to create like 3 different objects for each callback. With state machines, we have a single object which is reused throughout the execution of the suspending function. So there's like less pressure on memory allocation and garbage collector. Okay, so we call getUserAccountID and we pass the state machine as a parameter, so that when getUserAccountID resumes, wants to return a value, it will call resume on our state machine. So getUserAccountID calls resume on our state machine. The label is 1 because we set it to 1 before. So now we set it to 2 because the next time we'll resume from the place of code which is after get product count. We assign the count ID because we got the value in the resume function in the value parameter, and we call get product count. We also pass state machine again, and we do it again for send message. So we set label to 3. We call send message. We pass state machine as a callback. And now in state 3, we actually are in the before the curly brace, which is at the end of the suspending function. So we have to finish the execution of our suspending function. So what we do, we actually call resume on the callback that was passed as a parameter to the send audit message. So this is why you have here send audit message callback used, and the resume is called on that. So this is roughly how Kotlin compiler generates the code. And the nice thing is that you actually don't have to write, this kind of code with state machines yourself. You just write a regular code. So you can use any language construct in that code. You can use loops, conditional statements, exceptionally, whatever you want. And this is actually the strength of using coroutines over things like callbacks or promise objects. You don't have to learn any new API. All you have to do is you have to mark your functions as suspending functions, and the rest, there's no special API for accessing these functions. So, but at the end of the day, we actually sometimes you want to have access to this callback, because, for example, if you want to write a synchronous method, for example, you want to fire off some computation on some background thread, and once that computation is finished, we want to return the value from our suspending function. We have to have access to this callback. And this is where we can use something which is like basic blocks of coroutines, of suspending functions. And one of them is called suspend coroutine. So it's a suspending function which takes as a parameter a regular function. And this regular function has this callback parameter, this continuation, as a parameter. And we can use this parameter either directly in this lambda that is passed as a parameter of suspend coroutine, or we can pass it to some other thread or some scheduled tasks. And once the task is executed, we can call resume on that callback in some other thread. So let's try to write some code actually with this and see how it works in practice. So we're going to write a simple function, which a simple suspending function will wait for some time. So we'll call it mySleep. It will have a delay. So we're going to use the suspend coroutine callback. Right. So a callback now is of type continuation as we expected. And for implementation, we're actually going to use timer. So in Java, in the JDK, there is a timer class which can be used to schedule tasks so that they execute at some specific point in time or after some delay. And we're actually going to use it here. So we're going to schedule a task after this delay. And in this task, we'll just call resume on the callback. And the nice thing about a timer is that it actually uses only a single thread for all scheduled tasks, so that even if we have multiple coroutines running concurrently and calling this mySleep function, it will actually use a single thread for all those calls. So now we can actually try to use it. So let's try to call mySleep. So we're going to just wait for, let's say, 5 seconds, and then we'll just print a single dot. So the idea is this nice IDE which actually shows you where your functions can suspend. So here, for example, you have this marker which says that there is a suspend function call. And this is because here we call the suspend coroutine. Suspend coroutine is a suspending function, so mySleep can actually suspend its execution here. And the same applies for main, where you can see that there is this marker as well. But there is like also this problem here. So there's this rule that a suspending function can be called only from other suspending functions or suspending lambdas. So we can't really call directly mysleep from main. And to actually call suspending functions from regular functions, we have to use something which is called coroutine builders. So these are like these special functions which allow you to create a coroutine from a suspending function and launch that coroutine and execute it. So there's like a number of those coroutine builders. And one of them is launch. So launch takes as a parameter a suspending lambda. So you can use suspending functions in this lambda. And launch itself is a regular function, so you can call it from wherever you want. And launch returns a job. So a job is this object which allows you to manage the life cycle of a coroutine. So you can, for example, cancel this coroutine so that it will not execute, or it will just stop the execution. Or you can use a join function, which allows you to wait until that coroutine which was created from the suspending lambda, until that coroutine finishes its execution. So you can try to use launch in our code. So here we're going to use launch. Okay. And we're going to try to execute this. So it should wait for 5 seconds and then print a dot. So it actually hasn't waited for 5 seconds. And this is because launch tries to execute the coroutine in the background thread. So by default, it's like this thread pool, which is fork join pool, similar to fork join pool. And launch itself finishes its execution. The coroutine will run in a background thread. And so launch finishes its execution. The main function also finishes its execution. And in JVM, if the main function finishes its execution, and there is no threads, non-daemon threads running in the JVM, then the JVM will just stop. And here the timer will use daemon threads. So essentially, the JVM just stops executing. So what we have to do is we have to wait for the coroutine to finish its execution before we leave main. So we can call this join function that we've seen. So we're going to get the job, and we're going to call join. And now our functions should wait until the coroutine itself stops being executed. But join itself is also a suspending function, so we have like sort of an egg and a chicken problem. And this is where we can use a different coroutine builder, which is called run blocking. So run blocking is quite similar to launch. It also takes a suspending lambda as a parameter. But what it does is it waits for this suspending lambda to finish its execution before it itself finishes its execution. And also the value of the suspending lambda is actually the value of run blocking, the return value of run blocking. You essentially shouldn't really use run blocking in your code. It's nice if you want to do things like unit testing or demos. So we're going to use it actually here. So what we have to do actually right now is add this run blocking here. And now our code compiles, and we should have the behavior that we wanted. So after roughly 5 seconds, a dot should be printed, and it is printed. So we've got our first coroutine created and executed. And coroutines are sometimes called lightweight threads. And there's a reason for that, because threads, they actually execute some code, and sometimes they stop, waiting for something, and then they execute the rest of the code. And in coroutines, with suspending functions, we also have the same behavior. There's like a piece of code. A coroutine can be suspended. It's not blocked. It's not blocking a thread, but it's suspended. It then resumes its execution. And we can have like multiple threads running concurrently. We can have multiple coroutines running concurrently. So there is some similarity here. So if we call coroutines lightweight threads. What does lightweight mean? So to show you that, we're going to try to create like quite a large number of coroutines and threads and compare those two approaches and see for ourselves how it behaves. So let's start with coroutines. So we're going to create 100,000 coroutines. And we'll call jobs. So jobs. Now we'll have a list of jobs. So a list will be like 100,000 elements. And then for each job, we'll just wait for them to finish. So for each job, we'll just call join, so that will wait until it finishes its execution. So we execute, what we do is we execute 100,000 coroutines. Every coroutine will wait for 5 seconds, and then it will print a dot. So it ran for 5 seconds, and we have some dots here. So I'm not going to count them, but if we exit the presentation mode and we get to the end of the line, you can see here, I don't know if you can actually see here, but there's like 100,000 dots here. So it worked. So we have a code which ran those 100,000 coroutines. Now let's try to do the same thing with threads. So it's kind of very, very simple. In Kotlin, we'll get used to run blocking. Instead of launch, we're going to use thread. So thread is like this function in Kotlin which creates a thread and then runs whatever is inside this parameter of thread, this lambda. So we're going to create 100,000 threads, and each thread will start executing, and first it will sleep for 5 seconds, and then it will try to print a dot. So we now have not jobs, but threads. Unfortunately for us, thread also has a join function, which does similar things. So we just wait for the thread to finish its execution. So you have the same thing. You should have the same behavior as with coroutines. But the behavior is different. So what we have is out-of-memory error, unable to create a new native thread. So at some point, we just created too many threads. And the number of dots which are printed here is 2022. So it's a lot less. And this is because there's like a limit of the memory that my machine has, so I was able only to create that many threads. But here you can actually see why coroutines are called lightweight threads, because they don't take that many resources as threads. They don't need a separate stack. So the amount of memory is a lot less than for threads. Right. So and now we can create a sequential code with suspending functions with coroutines, but coroutines can also be used to create concurrent code. And for concurrent code, we need yet another coroutine builder, which is called async. Async. So async, just like every other coroutine builder, takes a suspending lambda as a parameter. It's a regular function. But what it does, it returns the value of this suspending lambda wrapped in a deferred type. So a deferred is sort of like a promise object. So it's a similar one. But this promise object has one function called wait, with which you can extract the value. But this function is a suspending function. So for promise objects like completable future or like those types from reactive libraries, you also have functions to extract the value. But these functions are blocking functions. They wait. They actually essentially block your thread until that value is returned, is delivered to this promise object. Here we have suspending functions, so our threads don't wait for the return value. They are just the coroutines are just suspended, and once that result is available, they just resume the execution. So let's try to write some code with this async and see how it works. So what we're going to do is we're going to create to simulate that we have two microservices. So one microservice will return personal details about the user, like, for example, a name of a user. And the other one will return financial details. Financial details. So let's say there is some amount to be in these financial details, and we'll create two separate functions for them. So we're gonna load personal details, and we're gonna simulate the microservice. So we're gonna just wait for some time with our mySleep function. So we're gonna wait, let's say, for 2 seconds, and then we're gonna just return some value. Let's say it's John. And we're going to create a separate function for financial details to simulate our second microservice. And the amount, let's say it's 120. And we're going to wait like for 4 seconds. Let's say it's a slower microservice. And first, let's try to run these functions sequentially and measure the time it takes to actually execute them. So in Kotlin, there is like this nice function called measure time millis, which allows you to measure the time it took to execute a piece of code. So we're gonna measure that time. And here we're gonna call first load personal details. Let's call it personal details, and then load financial details. And then we're going to just print the values. So name is personal details name, and amount as amount. Right. And then we're just going to print the time it took to actually execute those methods. So we call these two in sequence. The first one takes like 2 seconds. The second one takes like 4 seconds. So in total, we have like 6 seconds. And this is the result we have. And let's now convert the code to be run concurrently. So we're going to use this async coroutine builder. So we're going to call async for this and async for that. And now our personal details and the financial details variables, they are of type deferred. So we have to extract the values from this type. So we're going to use this wait function. We're going to call await. And the same for financial details. And that's about it. So now those two functions, they just run concurrently. So it takes now 4 seconds to execute this kind of code, because the longer one, the load financial details, takes 4 seconds to execute. And now you can see that the concurrent code is more complex than the one which was asynchronous but sequential. And this was actually done by purpose. So the Kotlin designers, the Kotlin coroutines designers, they think that concurrency should be put explicitly in your code so that it's visible for the developer that something here is not something here happens which is like not straightforward. Like with sequential code, even if it's asynchronous, it's still sequential. Like things happen one after the other. With concurrent code, there are things running in parallel, and if you put it explicitly in your code, then there will be like no surprise that something runs concurrently. So this is why we have to use such things as the async coroutine builder. So now we have our coroutine builders which we can use to run suspending functions concurrently in sequence, etc. But if you have a new project, then it's quite easy to introduce coroutines. But what if we already have an existing project which uses asynchronous programming? So for example, let's say we have a project which uses completable future. So we have an API which either expects completable future as its input, or you want to use coroutines in an API which expects completable future, and you want to somehow create this completable future using coroutines. And for that, there's like a set of libraries. So there is like this set of libraries called Kotlin X libraries, which allow you to interoperate with different kinds of asynchronous code, asynchronous libraries. And there is one for JDK completable future. There are other ones for reactive streams, etc. But the one for the JDK completable future, it allows you to interoperate with coroutines in two ways. So first, there is a coroutine builder defined, which is called future, simply future, and it will return a completable future. But as a parameter, it takes a suspending lambda, just like every other coroutine builder. So you can simply use suspending functions in your future coroutine builder, and because it returns completable future, you can use it in your application if it expects completable future. And the other way around, you can actually, there is an extension function called await. So extension functions in Kotlin, they allow you to, this mechanism allows you to create new functions on existing types. So like here, for example, we have an await function on completion stage. So completion stage is like this super type of completable future. So you can also call await on completable future. And this extension function, it's a suspending function. So if you already have an API which gives you the completable future, and you want to use this API in coroutines, you can just call await function, await extension function on that completable future. And since it's a suspending function, you will not get a blocking code. And the same thing you can do with RxJava, for example. So here there is code for RxJava 2 and a single reactive type. So there is Rx single coroutine builder, which allows you to create a single from coroutine from suspending lambda, just like future created completable future. Rx single creates single. And you also have this await function, extension function on single source, and the single source is like this super type of single. So you can easily integrate also with solutions which already use reactive libraries. So there are some things which are not covered here because the topic itself is quite broad. I just want to mention some things which, if you want to go deeper, you should probably learn more about these. So there's something called coroutine context, which it was actually on one of the slides. So essentially, coroutine context, it defines the context of execution of a coroutine. So if you, for example, want to specify that you want to use a special thread or some thread pool for your coroutines, then you can achieve it by using coroutine context. So all those coroutine builders, they actually have like these additional parameters which were not shown here because there are some default values for them. And one of them is coroutine context. So by default, it uses a coroutine context which is backed by a thread pool, which is like sort of like a fork join pool. But you can specify your own. So for example, there is a UI coroutine context, which you can use if you do things on Android. Because on Android, if you want to do some things which are connected with UI, you have to use a special thread for that. And with coroutines, you just specify this UI coroutine context, and the suspending lambda will execute in this special thread. Also, if you want to have a shared state, like in regular code, you use things like synchronized and locks. But these these components like locks, they have those functions which allow you to put a lock, to lock and unlock, but those things are blocking. So if you want to have a lock on an object and it's already locked, then the thread that executes is actually blocked, and you have to wait until this lock is unlocked. And in coroutines, you can use mutexes, which also have these lock and unlock functions, but they are suspending functions. So your thread will not be blocked. just your suspending function will suspend its execution, and once this mutex is unlocked, the suspending function will resume its execution. We have channels and actors. So coroutines can talk to themselves. And there is a concept of a channel. So one coroutine can send a message to a channel. The other one can receive that message. So it can be thought of as something like a queue, although there are like different kinds of channels. But the simplest one is like a queue. And there are queues in Java already. But those methods for putting something in a queue and getting something from that queue, they are blocking methods. So essentially, if you have an empty queue and you want to get something from that queue, then the thread just blocks, waiting for something to actually be inside that queue. With channels, you have also functions like send and receive, but these functions are suspending functions. So again, your coroutines will just suspend the execution. They will not block the thread that executes. And there are like libraries which allow you to interoperate with different kinds of existing solutions. So I mentioned, Completely Future and Devoxx Java. So there are libraries for things like reactive streams, like Guava or Quasar, and you can actually, easily create your own. So if you want to know more, there's a couple of places you can have a look. So the first one is this Kotlin X set of libraries. It's available on the GitHub repository. So there's like a nice set of documents there. So like tutorials, guides, etc. They are really very written in a very pleasant and easy to read way. So I suggest you to have a look at them. There is a website for coroutines in the official Kotlin language reference, and you can find some information there. And you can also Google Roman Elizarov. So Roman is the guy from JetBrains who is the main brain, like the main designer of coroutines in Kotlin. And there's a couple of videos of his talks where he goes a bit deeper about coroutines and its implementation and design decisions. So you can also have a look at those talks. And this is me. And there is on my GitHub repository there is a library called Spring Kotlin Coroutine. So it actually allows you to use Spring framework, allows you to use coroutines or suspending functions in a Spring framework. Just by declaring a dependency, you're allowed to do things like have suspending functions as web methods or as repository methods. So if you're interested, you can have a look at them. It's not an official project of Spring framework or Pivotal. Some of it has actually been ported to Spring Foo, which is like this new project from Pivotal for functional Spring. And more stuff will hopefully make its way soon to the regular Spring framework. So if you want to use coroutines with Spring, then you can have a look at that. So that's all from me for today. If there are any questions, I'm happy to answer them. There's a question up there. I can't really hear you, I don't know if there's a microphone here or if you can come closer. Do you have a microphone or something?
Why use Java time function class instead of coroutine delay function?
Yeah, so this is just to give you an example of that. I mean, there is already a function like mySleep, which is called delay, as you say. But I just wanted to give you an example of how you can write your own suspending function which access this callback. And it was like a very, very simple case. So this is why
I just want to add one note. Coroutines have a not trivial engine to handle exception in background threads. So if you want to throw a business exception from your background thread, it's very hard. to handle it.
There are like more things like deeply in the coroutines. So it was just the things I've shown you there, like just basic stuff. As I told you, I mean, if in any solution, if you go deep enough, there are some problems. But exceptions are one of them. Yep. So, any other questions?
Is there any other bottleneck?
Bottlenecks, like you mean like what kind of bottlenecks? Okay, so one thing which I always get this question is that coroutines actually are now called experimental. So this is an experimental feature. This is how it's called by JetBrains. But they are like experimental. They've been like experimental for the last a year and a half. And this was actually one of the mistakes they made when they called them experimental. Because I mean, the feature is working. The compiler itself, there are like not many changes in the compiler. Just new features are added, but it's pretty stable. The last, I think the thing that is not as stable as it could be is this Kotlin X libraries. These things like jobs, etc. Exception handling. They change a bit. But nowadays it should be pretty stable. So I think that in Kotlin 1.3, coroutines will no longer be experimental. So we have to wait a bit for that. But yeah, I mean, no, JetBrains uses coroutines in their own projects. They even released a web framework called Cater, which uses coroutines. So it's pretty stable solution. So you shouldn't really worry about if I use coroutines now, what will happen when they are, for example, non-experimental? Because even though some things will change, like for example the names of the packages for those types like job, etc., because they are now in the experimental package. JetBrains always, if they introduce a new feature and they deprecate the old one, they have this migration path. When for some time they support both solutions, and they also allow they also give you tools to migrate, and this will happen also for your coroutines code. So if you now use coroutines and use those experimental package types, then if they finally make its way to like a regular package, then IDEA will have like a migration tool which will just with one click allow you to migrate to a new API. Okay, another question? All right, thank you very much.